Hi guys, so welcome to part 2 of Let's Make TensorFlow, and in this part we'll be defining our input layer, our dense layer, our activation layer, right? And in the next part we'll be seeing how to make functions which add dense layers, which add input layers, activations and all that, the training loop and all that stuff, model.fit and all that. So here we'll just see how to define the input layer, how to define an activation layer, how to define a dense layer. Cool. So let's start by understanding what the thought process will be. So we have a list called nodes per layers, we have a list called output of layers, and we have a list called layer order, right? And we can just go without this for now, without this boolean. Nodes per layer will keep a track of how many nodes are there per each layer, as the name of the variable suggests. Output of layer keeps a track of the output of each layer inside your neural network. And layer order defines what order the layers are coming in, if it's dense, activation, dense, or is it dense, dense, activation, dense, or whatever order you want to do it. So this global list will take care of that. So we'll be making a class called model later, and all of these will be subclasses of this class called model. So let's start by defining our input layer. So input layer first will be a subclass of model, and now let's make a constructor, and the constructor takes in the input, that is input to neural network. So now what we are doing by writing this statement is that the global nodes per layer statement is that we are going to refer to this one, and if there is any nodes per layer variable used inside this function, we're going to ignore that because we want to talk about this. So we want to make changes to the global list, right? So once you have mentioned that both and output of the layer, again we're going to use the one which is global, so we need to mention that inside each function which we use. So now let's start writing the code. Here self.output will be equal to inputs to n. So input layer is nothing but the first layer of a neural network. So whatever comes in exactly goes out. There is no change. So the output of this will be the same thing, which is what is given to it. But there's just one thing which we need to be careful. That is, if type of inputs to n is equal to list, then we are cool with it, because that's how an input should be given. It should be given as a numpy array, but for simplicity I'm just going to keep it as a list. And if that's the case, then output of layers dot insert 0 self dot output. So why do we do this? So output of layers is basically storing the output of each layer. So the output of the input layer will be the first thing in that, because the input layer is the first layer. So what our output is coming from the input layer will be the first output which we need to store, because that will then be passed on to the dense layer and so on and so forth. So after this, let's say nodes per layer dot insert 0 inputs to nm. So basically what we do is, in output of layers we prepend, that is in the first part, in the beginning of the list we append output dot self dot output, that is what we are getting as input. And also in nodes per layer, which is the list which is keeping track of the number of nodes in each layer, we are gonna put the length of this. Next, let's say if it's not a list, so else, what do we do? So what we can do is we'll just raise an exception, and inside the exception we'll say ensure you provide the input in the form of a list. So that's how you raise an exception. Now, what is a forward propagation through an input layer? A forward propagation through an input layer will just return the same thing, self dot output, or we can say the input which is given to the input layer. So this is very simple, we can see, because it's very intuitive, because input layer is the most fundamental layer where nothing really happens. It's just an input, the same thing is given as output. But this is very important because this is the first layer of any neural network, right? Yeah. Alright, so now comes a bit more complicated part than the previous one, because it's the dense layer. So where the forward propagation is not just input equals output. Here we have weights involved, biases involved, and we need to initialize the weights and all those things. So let's see how that works. So we declared a class called dense. Again, it will be an inherited class from model. We'll be defining model in the next video, don't worry about that. Next, we'll have the constructor as usual and a forward function. So in the constructor, we'll say that nodes per layer, outputs of layer, and input layer, and let's just ignore this for now. We don't really need this. And these two, we are referring to the global variables and not any local variables. Once we have that, so even in TensorFlow, we know that if it's the first dense layer we're talking about, then we should always give the input shape, because if it's a second layer, then TensorFlow automatically calculates it. So we're going to follow the same. So if input shape is not given, then we are going to just assume that this is not the first dense layer. If input shape is given, we are going to assume this is the first this is the first dense layer of the network. So let's configure that first. So if input shape is okay, let's just say if not input shape. So if it's not none, then we just say self dot last layer nodes is equal to nodes per layer of -1. So basically it is, what we are going to say is that if it's not none, that means there has been a layer before this, right? And if there was a layer before this, we have this variable to keep track of that. So the last entry to this will be the number of nodes in the last layer. So that will be the input shape for this dense layer precisely. So else, let's say input shape is given. So then we're going to say self dot last layer nodes is equal to input shape, whatever is given. Yeah. Now once we have that, let's initialize some weights. So self dot weights, you can go with a lot of ways of doing this. I would strongly recommend you to read through things like Xavier initialization, HE initialization. These are all common strategies for initializing weights. I'm just going to declare it as a random normal distribution, so to avoid unnecessary complications. So np.random.randn, and now the tricky part. Now we should not mess up here. So the dimensions of this weight matrix will be self dot last layer nodes, comma, n neurons. So n neurons is the other input of this layer. So let's say we have a dense layer, for example. So we say 4 and input shape is equal to 4. So that means it has 4 nodes in it and the input shape is 4. So we're going to say we're going to have a 4 cross 4 matrix technically of random values, and we can just multiply with this 0.1. This is just a scaling factor. You can go for 0.01, but when I tried it out before, 0.1 was a more appropriate number to go ahead with. So once we're done with that, what we're going to do is nodes per layer dot append n neurons, because we need to keep a track of, as soon as this layer is declared, now we know that the last layer has n neurons in it. So the shape of last layer is n neurons. So we're going to put that into this list, because this list's job is to keep a track of how many neurons are there in each layer. Once we're done with that, we can go ahead and say self dot biases is equal to, you can go with anything here. You can go with ones or whatever you want. You can go with 2s or 3s or whatever you want. I'm just going to go with zeros because that's what Lord Andrew Ng said. So let's just go with zeros, and this shape of this will be 1 comma 1 comma n neurons. So yeah, this will be the shape of the biases matrix. Once we have that, we are pretty much done with most of the stuff, and let's go with the forward propagation, because we have declared the weights, we have declared the biases, we have appended to nodes per layer saying that we have updated this list saying that this is the last entry and this is the last layer. The lastmost layer currently has these many neurons. Now let's see how the forward propagation will work. So first, let's say we're going to talk about global output of layers. We need to mention that because it's a new function. After we have done with that, let's say self.output is equal to, so in a forward propagation in a dense layer, just for your reference, I'll pull up this article, and this is how forward propagation happens: weight into neuron into plus weight into neuron, and so on and so forth until the number of neurons are exhausted, plus bias. So when we come back to VS Code, we're going to do the same thing. So np dot output of layers. This one. Weights. Biases. So it's basically a dot product between the output of the previous layer, that is the input to the current layer, and the weights of the current layer plus the biases of the same layer. Now, once we're done with that, we can just say we can update this list by saying append self dot output and return self dot output. So basically, this dense class has a constructor which initializes the weights, just like how TensorFlow does. It has a forward propagation function which takes the outputs from the previous layer, does a dot product with the weights, and adds the biases and puts it onto the next layer. And we update these global lists called output of layers or nodes per layers. We keep on updating them as soon as a layer is created to avoid confusion. So we can see that in dense we did append, but for input layer we did insert. This is because the input layer has to come first and the output and the following layers will come ahead of it. So the input layer has to be first regardless of whatever comes next. So that's why we wrote insert and we are doing append here. And next, the activation layer. I didn't want to code this live because it's very obvious what happens. So let's say we have an activation function. So it has a constructor where we pass in the activation. So we can pass in the activation like this, for example, ReLU or linear or whatever it is, whatever function you want to give. You can just do a string comparison, and what you need to do is declare a forward function just like how we did before. Mention that you're going to talk about the global output of layers and not any other variables. Now, if self.activation is equal to ReLU, that is, if the input of this function is ReLU, then what happens? The previous layer, any output in the previous layer which is below 0 will be brought to 0, and anything above 0 will be left as it is. So I'm just going to iterate through the output of the previous layers. So that's why I took -1, because output of layers of -1 will be the output of the latest layer, because list of -1 is the last entry to the list. And inside that, if output of layers of that number of I is less than 0, then we are going to substitute it with 0. Otherwise, we don't do anything. And elif self.activation is equal to linear, we just pass, because linear activation really does nothing. Whatever your value is just pumped out, y is equal to x, right? So that's how you define an activation layer. So now we know how to define an input layer, a dense layer, and an activation layer. So to sum all this up, we have 3 global lists that keep track of nodes in each layer, outputs of each layer, and the order of how nodes are appended to each layer. This list will come in handy later, not now. We just need to be careful about these 2 lists for now. And the input layer just passes on the whatever is given as output. So the forward propagation is really simple. It just returns self output, and it appends whatever is given to output of layers. Sorry, it inserts, my bad. So it inserts in the first place. And when it comes to dense layers, we instantiate weights which belong to the size of last layer nodes, comma, number of neurons, and we multiply it with 0.1 as a scaling factor. Then we append the number of neurons in the latest layer declared to nodes per layer, because that is what the list is doing. It's keeping a track of how many nodes are there in each layer. And then we declare biases, and then we do a basic forward propagation where we have a dot product between output of the previous layer and weights, and we add it with biases, and basically we return that. So that is the forward propagation of a dense layer. And when it comes to activation, as I told you, it's very simple. If it's ReLU, anything below 0 becomes 0, anything above 0 is left as it is. If it's linear, everything is left as it is. So this is how you basically go about declaring the main and fundamental classes of TensorFlow, which help you through computation. And I hope this video helped you guys. And in the next video, we'll be seeing how to make functions like, let's say, model.add. So we declared dense, we declared activation. Now in the next video, we'll declare add, we'll declare predict, we'll declare fit. These 3 functions we'll deal with in the next video. So till then, cheers. I hope you guys like this video. See you in the next one.